Warm greetings to everyone joining us wherever you are. I hope everyone is well. So today what I'm going to do is I'm going to give you essentially a very brief introduction into neural networks, explain our product ROM AI. Then I'll go into talking about the kinds of systems that ROM AI can handle, which are static and dynamic systems, along with giving you sort of examples where you can view how various parameters within ROM AI affect the end result. I will also give you a small demonstration with the ball balancing table, which is what was used with the previous competition. And finally, we'll cover a few tips with regards to ROM generation in order to make the process a little easier. So ROM AI as a technology is based fundamentally on neural networks. And neural networks are quite intriguing in the sense that initially when we conceptualize them, they were a way for people to essentially mimic the human brain. That was the initial goal. But over the decades, that has evolved into more specific tasks, and the networks that we've developed have also specialized in order to solve those specific tasks. So we started off by wanting to mimic the human brain. So in that sense, we need to know what the human brain is made up of. So we have biological neurons, and these we consider the smallest functional units of our brains. These neurons essentially propagate electrical signals. So when a neuron receives some sort of excitation or activation that is beyond a certain threshold, it then propagates that signal in a way that is characteristic to itself. So these signals are propagated as electrochemical trails from one neuron to the other. And there is a contingency that the previous neuron has to create or generate a signal that is above what we call an activation threshold for the next neuron in order for the signal to continue propagating. So this is a very simple idea of chaining them together. So when we assemble this into a network, it results in a product where you have specific inputs activate specific outputs. So if you can imagine yourself wanting to blink, the end result would be you blinking, or you wanting to move your arm, then the output would be you moving your arm. But it's the neurons that are responsible for this particular propagation. So analogous to this, we have artificial neural networks. So they're inspired by our brain. And what happens here is inputs are weighted and summed together, and then they are fed to what is called an activation function. And this activation function is simply a mathematical relation that controls how the input, the summation of the inputs, is transformed. So the activated neuron produces this output. And this sort of basic computational unit is what we call a perceptron or artificial neuron. And when we link multiples of these together in a network as such, in multiple layers, then we begin to be able to mimic certain decision-making abilities of the brain. So what we can see here, the multi-layer perceptron, is essentially what we consider a neural network. And the functioning is quite the same. So we have inputs. The inputs trigger the activation of some neurons and possibly not the others. And this propagates forward, resulting in an output. So to briefly cover what an activation function is, it's simply a mathematical relation that decides whether or not a artificial neuron will fire or produce an output signal. So we have different kinds of activation functions. So we have the rectified linear unit, we have the logistic regression or the sigmoid function, and the hyperbolic time function. what you notice about these three is they are non-linear. And even though you notice that the rectified linear activation unit is piecewise linear, as a whole, the function is non-linear. And then we also have a simple linear activation where the input is equal to the output. So the purpose of the activation function is to help include this thresholding of sorts, where we decide whether or not neurons activate. So in order to get a neural network to work, or in essence, if you think about our brains, in order for us to learn to do a specific task, we train ourselves. So what does it mean to train a neural network? So what we do is we provide this network with certain inputs. Then we obtain the outputs that the network produces. And then we compare these to expected outputs, and then we use the differences from some sort of loss function or some sort of corrective input to correct the network's prediction. And this is quite analogous to how we learn as human beings. So we have a certain expectation of an output for a task that we perform. We provide certain inputs, and then we observe whether or not we were able to achieve this output. And if we aren't, then we try and correct ourselves to the extent that we can accurately achieve the outputs that we desire to achieve. So what is the purpose of a loss function? So the loss function mentioned earlier, it's simply a mathematical function that computes the accumulated prediction error over a training period. And when it's large, it simply means that the predictions simply do not align with the expected outputs. So the primary goal of training a network, or what we call training, is to minimize this value of loss. And the way that this is done is slightly more involved, where the loss is used to adjust certain parameters within the network. Ideally, this should lead to the network making more accurate predictions in the next training cycles. So we have ROM AI. So there is this acronym in the title, which is ROM. So then the question comes up saying, what exactly is a ROM, or a reduced order model? So quite specifically, it's just a technique for reducing computational complexity of a mathematical model in numerical simulations. So it's a simplification of a high fidelity. High fidelity in a sense, the system is able to very accurately replicate or predict outcomes. So it's a simplification of such a system or a complex computational model. So there are approaches to making reduced order models. So one is either a model-based approach, or the other is a data-driven approach. In a model-based approach, you have a model, a computationally complex model, and you can apply certain numerical techniques in order to reduce the size of this numerical problem, and therefore reduce your computation. And the other approach is a data-driven approach. So with a data-driven approach, you simply use data from an underlying real-world system to recreate your system numerically or computationally. So why are ROMs important? Why are they beneficial to us? So in cases where a physical system is not available for testing, the ROM serves as a high-fidelity duplicate. You can imagine this being the case when the physical system is not yet in existence. Say you're prototyping something like aircraft structure or something of that sort. So here, the ROM serves as a very accurate real-world duplicate of the structure based on numerical data, numerical simulation data that you can give it. It significantly reduces computational time. That is its purpose. And the focus now shifts from basically focusing on whether or not your computational model is accurate towards achieving your design goals for your control system and etc. So ROM AI is an Altair product available through Activate. And Activate is available to all of you, provided you've applied for student licenses. So it is a very simplified approach to AI. So it makes the process much easier for us. So the objectives of ROM AI are basically as follows. Since it's a data-driven approach, we require data, and then we use this data to create a high-fidelity model based on the data that we can then use in our Activate models as a substitution for either a numerical model of some sort or anything of that kind. So it has various applications, and these are the applications that we have spelled out so far. So we have thermal, electrical, fluid, mechanical systems, and we also have essentially discrete elements, which is, you can imagine piles of lumps of certain sort, basically in material handling. So what's happened here is either numerical data from real world simulation, real world data collection, like in the case of the demo shown here, or from various numerical analysis was used in order to train a ROM. And then we've compared the results. And essentially, we can create high fidelity, low computational cost models. And then these can further be used to refine other aspects rather than numerical models. So our basic workflow for ROM AI is as follows. So we start with data from either real world systems or simulations. This data is then fed to ROM AI, and in ROM AI itself, we can train a neural network or a ROM. We can then use this ROM AI block, as I mentioned earlier, in a model in Activate, and then we can eliminate this computationally expensive aspect of our model and focus more on our other strategies. So this is basically what the ROM AI GUI looks like. Switch over. So when you open up Activate, I hope my screen's visible now. This is what you'll be met with, which is an empty model. So in order to get the ROM AI, to have access to it, we simply go to File, Extension Manager, and then if it isn't switched on, you'll have to switch this on. You'll have to enable that extension. And I believe you might have to restart Activate. But after doing so, you'll have this button here, which is ROM AI Director. ROM AI Director is nothing but the GUI that we use to train ROMs, along with other things like view results and then do our time simulation. We also have this preprocessor available to us. I'll go over the specific the entries and the options through this presentation and later in the demo also. So now the thing about ROM AI is we specifically use it to handle two sorts of systems that we encounter. So we have static systems and we have dynamical systems or dynamic systems. In a static system, you see that the output of your system is only dependent on the input and of course the characteristic parameters of the system. So these characteristic parameters are essentially like numerical values which can be used to accurately create a mathematical model for your system. So as you can see in a static system, the output is only dependent on the input because your characteristic parameters for a given system are fixed. And then we also have the dynamic or dynamical system. In this case, the difference is the state variables. So your state variables are nothing but parameters which describe the current state of your system at this point in time. And these are very important because your output now depends on the current state of the system as well as the input. And the example of such a system, is basically any real world system where you have effects like inertia and etc. to consider. So, yeah. So another way that we classify systems, at least dynamical systems, are based on the state variables. So if the mathematical formulation is a linear combination of state variables, as in this case, for a mass spring example, then we say that the system is linear. But if it's described by a set of non-linear equations, then we say that the system is a non-linear dynamical system. In this case specifically, it is non-linear because of the sine function in the case of the pendulum. So that is the non-linearity. And we handle these differently within ROM AI. So we'll just go over static systems and requirements in terms of what sort of data we'd need. So since ROM AI is a data-driven approach, we do need data. And in the case of a static system, we just require the inputs and the outputs. And due to the way that ROM AI works, we also have to have a dummy time column. So the very first column in your data will have to be labeled time, and it will have to have some sequential numerical data starting off from 0 or higher. So what is a static system? So they are essentially systems where you can ignore transient behavior for one. And as mentioned earlier, the output is not dependent on any sort of current state of the system. So it's only dependent on the input. So if you think of a purely resistive element in an electrical circuit, that is sort of a static system. Or systems where the dynamics with respect to the time window that you're interested in are very short. So in the case of opening a valve for incompressible fluids, so when a valve is open a certain amount, the flow rate is X. And if it's open by another certain amount, the flow rate changes to Y. So one example of a static system that we'll go over is simply this polar sinusoid. So here we can see that the value at any given X and Y coordinate is not time dependent or state dependent. It just depends on the X and Y values. And that gives us an output. So this is data that was collected to train a ROM, and the range of data was very negative and positive 5 for both the X and Y. And since it's a sinusoid, the output values range between -1 and 1. So this is the example we're going to keep in mind for the upcoming pointers. So as I mentioned, we have these activation functions, which are the ReLU and the tan hyperbolic, which is used by ROM AI. So for the next couple of slides, we'll look at the ReLU function and how using the ReLU along with some other parameters affects our ability to predict the output. And then we'll take a look at the tan hyperbolic function. So here we have a parameter called the regularization coefficient. In the cost function, this regularization is just it's a fixed parameter wherein you add a certain component back to your loss function. And this added component essentially causes more correction in that sense. So we can see that we have no regularization, and here the system, although it's not great, it sort of is beginning to look like the initial data that we provided with. On the other hand, if we add regularization, we see that the whole output is just flattened. So increasing regularization has this effect of squashing the predictions or the output of the system. Now we have hidden layers. So in a neural network, we have the input layer, we have the output layer, and then all of the layers in between, all of the layers of neurons that we have in between, Those are what we refer to as hidden layers. So if we look at how the number of hidden layers, 2 versus 6 in this case, affects the output, we can see that adding more, it has the effect of sort of smoothing the response, but at the same time, increasing the degrees of freedom or the ability of the ROM to more accurately predict the data. So if we go considering the number of neurons per layer, here we have an example where we have 50 neurons in each layer versus 100 neurons in each layer. And we see that adding more neurons, it has this effect of increasing the fitting capacity, although this is not always true. Right. And another thing I should mention is, if you've noticed, most of the ReLU function responses, they seem to be discontinuous and very planar. So this is a characteristic of the sort of response that you get from ReLU, wherein the output is essentially approximated by a larger number of planes. These planes are stitched together, and the network tries to approximate the outputs of them. So adding more layers, more neurons generally has the effect of adding more of these planes and smoothing the output. So here is just a basic results sort of comparison that we can give you. The instance evaluation and this output, these are features available in the view and the timesim tab in the GUI that we can go over later. Now we move on to the tan hyperbolic function activation function. So one thing you immediately notice with using the tan hyperbolic function is that the response is much smoother. But again, increasing the value of regularization coefficient, it has this effect of squashing or flattening the response. So you've gone from like a smooth 3-dimensional curve to a more planar response. Adding hidden layers, it has this effect of more smoothing the response and at the same time increasing the degree of freedom of the response surface, which means the response surface becomes more flexible and better able to predict output values. And here with the number of neurons, what happens is if we increase the number of neurons per hidden layer, it doesn't necessarily increase the fitting capacity. Sometimes it might make it too rigid and less flexible. So here we have just the representative results page from the TANET simulation, and we can sort of see that the predicted values in certain spots don't exactly coincide. And this is the result of using a large number of neurons. So here it sort of tends to decrease the flexibility. There is a warning though, in the sense that you should always keep in mind that the data that you feed ROM AI is essentially what drives the output. So ROM AI can only make reasonable predictions in an area where it has seen data. And just to drive home that point, this is what the polar sinusoid looks like if you proceed outside of the interval we initially suggested. That we initially collected data in, which was -5 to 5 along x and y. And this is the effect of ROM AI making predictions outside of the scope of data that we gave it. So we can see immediately that it doesn't really make that much sense. We don't expect any sort of sinusoidal function to have a value above 1 in any case. But this is what happens because ROM AI is now making predictions in an area where it has never sort of seen data. So outside the region, the predictions become unbounded and they tend to deviate from reasonable expectations. So one way to get around this is just to collect more relevant data in terms of your system. And this is another static system that is just a parabolic shape in the x direction. So This specifically is for a comparison of tan hyperbolic versus the ReLU activation functions. And it's evident that using tan hyperbolic results in a smoother response surface rather. And ReLU, as we mentioned earlier, essentially imitates this response with the use of these broken planes. And just going over results of the tan hyperbolic, and we can see that it has a relatively good prediction ability. So we have considerations for a static system. The ReLU activation function approximates the response with broken hyperplanes. Tannets generates smoother, more continuous response, but is possibly less flexible. For problems with a more regular response and not a lot of slope changes, tan hyperbolic allows you to get better results with mesh neurons. And since ReLU must approximate it with Broca hyperplanes, you generally have to add a lot more neurons. For nonlinear problems, it's good to try both activation functions before you invest time in essentially exploring one of them with a larger number of neurons and layers. And this is important to keep in mind because the training process can take time. So from here, we move on to dynamic systems. Like we stated earlier, dynamic systems are nothing but systems where the output depends on both the input as well as the current state of the system. So along with specifying state variables for a dynamic system, there is the option to also specify physical constraints, as in how the state variables are related to one another. So here we can see that we have displacement and velocity. So the physical constraint would simply be saying that the derivative of displacement is velocity. And because ROM AI is both the systems modeling as well as a reduced order modeling tool, this additional information is helpful, although it is not necessary. So what sort of systems do we call dynamic systems? They're essentially slow, where the system's inertia matters, like thermal systems, mechanical systems. Right. So one example of a dynamic linear system is a two-mass system. It's a simple mass spring damper. Two of them arranged in series. And the values of the spring constant and the damping coefficient are constants, so they don't change. And this is why the system has a linear behavior. The data in this particular case was captured through an Activate model. And this was the data used to train the neural network. So here in this case, since we know that this system is linear, we could simply set the network architecture activation to linear. And that's it. So the evaluation, here's how we can evaluate the output of our trained ROMs, which is something we'll also revisit during the live demo. So essentially here you have an accuracy check, which gives you an R-squared value. So with R-squared values, the closer you are to 1, the more accurate your system can recreate the initial data. So in both these cases, you observe that we have a value that's very, very close to 1. And in addition to that, we can also plot a time simulation based on input data versus the ROM's predictions. So here you can see that the ROM's predictions are essentially overlaid onto the data set, or rather vice versa, which is why you can't see it. And this in general is a good sign. In addition to this, we have a network that we set up where we can place the ROM AI block, and then we can test its response to inputs, and again compare it to the real system. And again, we can observe essentially an overlap between the values, which is a good sign. And this is precisely what we aim to do with ROM AI. So now that we no longer have to calculate individual values, we're all set with that. So this computation is much faster than the old system. So the considerations that we have for dynamic systems is hyperplanes are not available if your state variables and outputs are the same. But if you have an output that is different from the state variable, then you can visualize it with the hyperplanes. If you set physical constraints, they are used in the learning phase, and it helps you get a more efficient ROM AI, but physical constraints are not mandatory. Due to the way that neural networks work, it will accommodate even you not specifying physical constraints. When defining input signals to generate a training set or test, you use standard inputs. So just by providing standard inputs in your simulations, you can generate a decent training data set in order to train your ROMs. So for highly nonlinear systems, you need more input shapes, or rather, you need to collect data in the nonlinear areas of your system in order to better train a ROM. Nonlinear systems in general are very difficult, and the ball balancing table we cover will be an example of a nonlinear system. So a small error in the estimation of one state is then propagated forward, which makes it difficult to have essentially accurate predictions. And if you use a deeper neural network with a smaller number of neurons in each layer, starting with the regularization parameter of 0 and a fairly large number of epochs, then you can sort of reach a very good network configuration with about 6 hidden layers and 5 neurons each, although this is not standard, it's a recommendation. So now we'll talk about the ball balancing table. So what is the ball balancing table? It's just a physical system that's used to teach control theory. It consists of a ball table with some sort of positional feedback. In this case, it's a 2D resistive touch sensing surface. And there are servo motors which control the tilt of the table in the X and Y direction. Some of you may be familiar with this, but it's used to teach the effects of different controller types on the system. If you've heard of PID controllers or proportional or PI controllers, etc. And now we move on to discussing what a digital twin is. So we have a real world system, which is the ball balancing table, and this we can acquire data from, which is how the ball moves and with what velocity based on how the servo motors are positioned. But we also have an entirely digital model of this. And this was available in the contest as well last year, if I'm not mistaken. So the model captures all of the physical properties of the real world ball balancing table. It has the same geometry, the same component contact and friction also. It has the same component inertias, which means you can accurately estimate how long it would take to move in a certain way. And it also includes the external body forces like gravity. So the ball's position and the velocity is calculated from inputs to the model as servo motor rotation. So in this case, the simulation can also output the position of the ball and the rate of change of the ball's position with respect to the input. So how do we use the ball balancing table digital twin to generate a ROM? So one way of obtaining your data is from a physical system itself. If you can data log from the system, that's great. But another way of doing it is to have either a digital twin or a FEM model or something of that sort. So data generation can essentially be the capture of data from this digital twin MotionSolve model. MotionSolve is another Altair tool that deals with multi-body dynamics. From this data, we can generate a ROM using the ROM AI tool. And this ROM essentially results in us having a twin of the plant, which is not as computationally expensive that we can use in our Activate model, and it mimics the behavior of the digital twin. So I will quickly move on to just showing you how. Yeah, this is the the original model that was used to capture data. And here, a set of arbitrary inputs were fed to a controller. The controller provides inputs to this motion solve model. And the motion solve model then generates outputs in terms of the ball's position and velocity. And all of this data is then stored to a CSV file. As you can see, we have the time column. We have Tx and Ty, which is basically the servo motor rotation. We've also, in addition, collected this data, which is the reference position of the ball or the intended position. But what we really require is here, which is the XY position of the ball and the X and Y velocity, along with our inputs. So from our motion solve model, we launch ROM AI Director. And this is where we cover training. So in order to train, we need a data file. So this data file is what we load up. And after loading up, it immediately tells us what the data set size is. In addition to this, we need to specify a folder where we want to save all our ROMs. So this is the folder where all of the various ROMs that you generate will be saved, and we need a name. So after this, what we have to do is we have to pick the data of interest. So we have our inputs, which is the X and Y rotation for the servos. And then we have our outputs from our system, which are the position of the ball and the velocity. In addition to this, these are also our state variables, because if you think about it, the position of the ball at some time, whatever that time may be, depends on the velocity that the ball is traveling at, and also the previous position of the ball. So these are what become our state variables. And then we can also specify physical constraints. So here we have the state variable and the linked derivative. So in our case, the derivative of the X position is the velocity. So that is X dot in our case for our specific data. And similarly, we have Y dot, which is the derivative of the Y position. So now another important aspect of training a ROM AI is the network architecture. The network architecture is quite simply the size of the entire network and how it's arranged, how many layers there are, how deep it is, and how many neurons we have per layer. So here, just as the initial value, we'll select a ReLU. We know we want to capture a nonlinear system with 2 hidden layers and 20 neurons each. In addition to that, we have training parameters. So here is a handy tip when it comes to the number of epochs you want to send. And this is based on the size of your data and etc. So starting small is always good. And you want to sort of look at how your ROM trains initially to get a feel for how values change and where they reach. Another thing we want to do is set regularization to 0. And the learning rate is, as the name says, it's the rate at which you expect the internal parameters of the network to update. So setting this too high can lead to a very unstable output, and too low will lead to a network that learns very slowly and takes a long time to train. Initially, we recommend you start off with the default value. And finally, you have the cross-validation split and the test split ratio. So the way that training works for neural networks is that there is some data that the network has never seen. And essentially, this serves to validate the network. So after training it, you provide it the validation data and you see how it behaves. And if the behavior is very poor, then you go back to training it again. So these parameters decide how your total data set is split between validation and testing. So once you're here, all you have to do is simply hit train, and then ROM AI will start running in the background. And this process can be very slow and very intensive depending on the dataset size and other parameters that you set. And another thing to remember is to initially, when you're starting off, set a lower number of epochs because you currently cannot stop training once it's begun. Another way to handle that is to select an early stopping criteria. And this is where you simply say, we want to monitor the value loss for the network. And this is the value that you pick as a minimum improvement. So if the loss stays under this value for these many epochs, then essentially it's like saying training isn't giving you better results, so we might as well stop. So early stopping is your useful tool, but only once you figure out what the nature of your system is. So here you can see that we have 8 to the 10 to the minus 4. So setting a value this large would not be good. So we go for a smaller value, and that would essentially take care of the leading point. So after training a ROM, we are brought to the viewer tab. In the viewer tab, you can view the architecture of the ROM that you trained, the inputs, the outputs, the states, and how you specified everything. In addition to that, you can also view the loss metric for various inputs, as well as the training accuracy. So in a system where you've specified physical constraints, only the derivative values are available. And yeah, in order to use this, you have to load up the file that you used. Same CSV file that provides your data. And then you can plot. And in our case, you can see that the R-square value is negative, which is not a good sign. But that is the challenge of replicating a system, which is where you can you essentially need to work on your network parameters. So I will demonstrate a ROM that was trained in advance. I hope this is visible. So this is a simple model that we set up to test whether or not the ROM can recreate the initial behavior. If we run this, we simply ask to pick a time period. So we'll go with 30 seconds, which is nice and slow, and parameter value. So here, essentially what's happening is we feed X and Y positions, and then the ROM AI will simulate and give us our outputs from the ROM. So something we can see here is that it's actually following the path that we specify in a reasonable manner. And we can try and validate our ROM by providing other inputs that we have a different value. And so this essentially, now we've created a reduced order model block here that is capable of replicating our system accurately. And all we've done is, in order to use this, you drag the ROM AI block into your activate model, and then you select the parameters and then pick the particular ROM that you trained in order to evaluate it. So I'm sorry for all the window jumping. Right, as you were saying. So that was a demo, and the results that we have based on some arbitrary path that we set for the ball, and comparing motion solve to the ROM that we generated. We can see that there's quite a high correlation. So this is essentially what a nicely trained ROM would give us. So we are able to accurately mimic a digital twin with this ROM, and the model is computationally very inexpensive. The motion solve simulation will take quite a long time because there are a number of calculations involved. So finally, we'll go to some advice on ROM generation. Typically for physical problems, we have 2 to 3 layers tend to be enough. But if you have some very nonlinear problems, then we can go up to 5 or 6 layers. But in general, it is better to have less layers and a fewer number of neurons, because that aids in the whole the point where you want to reduce computational costs. A larger net will more likely suffer from poor generalization properties compared to a smaller one. This is also another issue with using a very large neural network. The regularization coefficient that we talked about earlier, it helps increase generalization. But simultaneously, if the coefficient is too large, then it also tends to squash or flatten your entire response. The ReLU activation function can be used in the first attempt to generate a romAI for a nonlinear problem. And this will produce a good enough response initially. And then you can proceed to moving to, say, a tangent activation function. With highly nonlinear problems, tan hyperbolic functions tend to outperform ReLU functions. But again, this isn't a generalization. It's very specific to the neural network that you end up making with the number of hidden layers, etc. With highly nonlinear problems, the tan its activation function. Oh, sorry. Like I said earlier, early stopping can greatly reduce training time. But this requires familiarity with the model. So initially, we recommend that you run it for a smaller number of epochs just to gauge what sort of results and losses the model produces. So properly setting these criteria will depend on that. For linear problems, you could simply use the linear model type, and then you don't have to set the activation function or the number of hidden layers. So with the linear model type, romAI just defaults to a simple linear regression. So we'd like to see all attempt non-linear problems as far as possible, but still. So when using state variables, you could have a problem and errors thrown up when there are duplicates in the training set. And this might either happen when you collect the data or when you put the data together. So that's something you should be careful of. It's also something you can easily eliminate if you're using Excel. And also, surprisingly, this should be mentioned, but units across all of the variables that you collect should be consistent. Otherwise, this tends to produce very non-physical results, and that can be confusing. So with that, we come to the end of this presentation, and we'd be happy to hear any questions that you have.